All right, welcome. Today, we're going to dive into something that's kind of invisible, but it's one of the most powerful tools in all of science and engineering. I'm talking about approximation. It's the art of being almost right, and you're about to see how it's pretty much the secret sauce that makes our modern world even possible. Let's get into it.
So let's start with a really big question. How do you even begin to calculate something as wild as the air flowing over an airplane's wing, or the way starlight literally bends when it passes by the sun? These things are, well, they're infinitely complex. They exist in the real world, sure, but the tools we use to understand them, they just aren't built to grasp that kind of infinity directly. And that's because we're living in two different worlds. You've got the real world, which is continuous, messy, and has infinite detail. And then you have our computers, our most powerful tools, and they are the complete opposite. They're all about discrete, finite, orderly bits and bytes. It's like they're speaking two totally different languages. So approximation isn't just a clever shortcut, it's the translator. It's the essential bridge that lets these two worlds talk to each other. Okay, so that brings us to our first big idea. When we talk about approximation, we're not talking about making a mistake or being sloppy. No, this is a deliberate and incredibly powerful strategy. It's the art of being good enough to get an answer that's actually useful. And look, this isn't just some random guesswork. Oh no, there is a whole field of mathematics dedicated to this called approximation theory. It's basically the science of taking a wildly complex function, something from the real world, and swapping it out for a much simpler one, like a polynomial, that a computer can actually get its head around. And, crucially, it's also about carefully measuring the errors you create when you make that swap. Now, check out this quote from MIT, because it sounds totally backwards at first, right? An approximate model can be better than an exact model. How does that make any sense? Well, think about it. An exact model of reality might be so ridiculously complex that no computer on Earth could solve it, and our brains definitely couldn't understand it. An approximate model, on the other hand, well, that's something we can actually use. It's what lets us understand things and, build stuff. So here's the name of the game. We're on a hunt for a simple function that can mimic the real messy one as closely as possible. The perfect approximation is one where the error, that's the gap between our simple model and the real deal, is as small as it can possibly be across the board. It's all about finding the absolute best, almost right answer you can.
Okay, so how does this actually work in the real world? Let's make it concrete. We're going to look at two different ways engineers turn messy reality into something a computer can solve. You can think of it as two different ways of putting the same puzzle together. So on one side, you have the finite difference method. This approach basically lays a simple, rigid grid of points over the problem. On the other side, you have the finite element method, which breaks the problem down into all these little custom-shaped elements, kind of like puzzle pieces. Right away, you can see why the finite element method is way more flexible for modeling all the weird curvy shapes you see in the real world. Let's zoom in on the finite difference method for a second. It's really clever in its simplicity. You just lay down your grid, then instead of dealing with complicated calculus, you just approximate it by looking at the simple difference between values at neighboring points. And just like that, you've magically turned one impossible calculus problem into a huge system of simple algebraic equations that a computer can just chew right through. But the finite element method is the real powerhouse of modern engineering. Because it uses these custom puzzle pieces, it can accurately model almost any shape you can dream up, from a car's frame to the blade of a jet engine turbine. It's definitely more complex to set up, but its power and flexibility are why you see it used in pretty much everything today. But, and you knew there was a but coming, right? This incredible power comes with a bit of a dark side. The very act of approximating, of translating the world into finite bits, introduces tiny little errors. And sometimes, those tiny errors can grow into very, very big problems. The main villain in this story is something called rounding error. You know how a number like pi has an infinite number of digits? Well, a computer doesn't have infinite memory, so at some point it has to chop the number off. That tiny little bit that gets left behind, that's rounding error. It's an unavoidable part of using digital machines. So let's look at an example. Imagine a simple calculation. If we round our numbers just a little bit, the final error in our result is maybe 1.5%. Okay, seems pretty manageable, right? No big deal. Yeah, but watch what happens when we use those same slightly off numbers in a much longer, more complex calculation. Boom! The error doesn't just add up, it compounds, it snowballs, and it explodes to over 15%.
This is exactly how a long chain of computations can amplify tiny, harmless-looking rounding errors into a total disaster.
And rounding error isn't the only ghost in the machine. You've also got stuff like underflow, where a number gets so close to zero that the computer just calls it zero, and then your whole program crashes when it tries to divide by it. Or overflow, where a number gets so huge it just breaks the calculation. And then there's this nasty thing called poor conditioning, which is basically when your whole model is so sensitive that the tiniest little change in the input sends the output flying off into crazy town.
So does all this mean that approximation is a flawed tool? Not at all. It just means you have to respect its limits. When we understand the dangers and know how to handle them, approximation becomes this imperfect but absolutely essential superpower.
And just look at what this superpower has helped us build. It's how we confirmed Einstein's theory of general relativity by calculating the bending of starlight. It's how we designed the microscopic pits on a CD to hold our music. It's even how we can use something as simple as a falling coffee filter to understand the complex aerodynamics of an airplane. Approximation is literally everywhere.
So really, at the end of the day, we have to accept that we're never going to have a perfect one-to-one model of reality. It's just too complex. But by strategically embracing this idea of good enough, by choosing our simplifications wisely, we gain the incredible power to actually understand and shape the universe around us.
And that leaves us with one last big thought to chew on. Is so much of our progress, our deepest understanding of the cosmos, is built on this foundation of being almost right? What does that really tell us about the nature of knowledge itself?